This is AP Chemistry lesson for Friday, September the 13th. This is the lesson you were given in class on Friday. It's due on Monday. So here's your solutions. Again, as always, you have to attempt the problems on your own. This is not a copying exercise, or you get nothing out of it and you don't prepare yourself for the AP exam. So do this as it was tended to be done, and you will, I hope, gain something from it. Okay, first thing we do, you're going to see some review type problems. So let's go ahead and do these. It's asking us to draw. Okay, so it's asking us to draw the Lewis dot structures for a number of elements. So I've created a solution sheet here. Yours does not have the space. So I do ask that you do this on lined paper. All right, so let's go. Carbon. Carbon is the fourth element over in its row. 1, 2, 3, 4. That means it has 4 valence electrons. Those electrons would be in the second orbital. So we're going to go around the world like this, and you're going to see this is what makes carbon such a significant element, is that it can bond on all 4 sides with those 4 unpaired electrons. Next, we're going to do lithium. Lithium is the first element in its row. It doesn't matter where you put the dot. I just happen to put it at the bottom. Next is helium. Okay, and I like to put these together to show that they're paired and that you can, the first orbital cannot fit any more electrons. Other Lewis dot structures might show them in different locations. I think that's not correct because it implies that they can be bonded. They can bond. Okay, let's just get through these then. Oxygen is 6. Okay, argon being a noble gas has a full octet. All right, let's move on down and let's do a significant figures problem. Let's just practice these a little occasionally each day. I won't give you one of these every day, but let's go ahead and see how we do this. So PEMDAS says we do this first, and that is a decimal point without a leading 0 on it, so watch that. Okay, and that gives me the following answer. This is my calculator answer. You don't round anything until the very end, unless it's a ridiculous number of digits. This really is bordering on a ridiculously large number of digits. It's not going to be, the significant figures are not going to be nearly that, but I went ahead and wrote down the full thing, which you really should do. Now we're going to add this to it, so I'm just going to write that number down here. Oh, and neglected to do something. How many significant figures do I have? This one is 9.020. Okay, that trailing 0 is significant because there's a decimal point, so there's 4 significant figures. And this simply has 3 non-zero digits, so those are all significant. So my problem cannot have any more than 3 significant figures at the end. Doesn't mean it's going to have 3, but it can't have any more than that. So now we're going to move on to add the 2.1, and all of this just carries down here. Okay, so you end up with 9.15364, and we say, where is the least number of digits? We don't count significant figures. Where's the least number of digits after the decimal? It's right here. So I'm going to draw a line straight down through there. So at this point, then, the only digits that are significant are these 2. Okay, anything to the right of this line is not significant. However, I'm going to use this digit to round this digit. And since it's a 5, it rounds up. So the final answer is 9.2. All right, go ahead and do this one, scientific notation, a couple quick scientific notation problems. We won't practice these a lot simply because you're going to do them so much in this class, they will become very natural to you. So 6.02 times 3.2 is going to give us 19.264 times 10. And it's -5 plus -2 gives us -7. Okay, now this is not a number between 1 and 10, so we need to move this over to there. So we make this number smaller, so we got to make this number bigger. Bigger on a negative number is going in the positive direction. So it's going to be 1.9264 times 10 to the -6. And now if we're concerned about significant figures, there's only two significant figures in the 3.2, so we can make that 9.2 times 10 to the -6. So as far as I'm concerned, either of those answers is fine. Okay, we move over here to a division problem. All right, so we're going to divide 9.87 divided by 0.67. All right, and that gives us 14.731 and a whole lot more digits that I'm not going to write. And it's times 10. And be very careful on these, okay? Even if you're good at math, I would write this down. It's 3 minus -5. So that's going to be 3 plus 5. So that's going to be 10 to the 8th. Okay. Now, I've got to adjust the decimal. I'm going to make this smaller. But I have to make the 8 bigger. So it's a positive number. It goes up to 9. And if we're considering significant figures, there's two significant figures in 0.67. So I can round that to 1.5 times 10 to the 9th. All right. Okay, let's keep reviewing these definitions. Some of you are still having, still learning them, and that's fine. So let's go through them. So a cation is a positive ion, and it's always good when you have a definition to have an example in your head. So for me, it's sodium. So sodium tends to lose electrons because it has low electronegativity. I'm sorry, I didn't write ion. It's a positive ion. So sodium, Na+, okay, is a cation. An anion, example of that would be, it's a negative anion, first of all. And an example would be F, fluorine, with a minus. Fluorine tends to want to pick up an electron. So sodium wants to lose an electron to be like the nearest noble gas to it, which is neon. And fluorine wants to gain an electron to be like the nearest noble gas to it, which is also neon. So they both end up with what's called the electron configuration of neon. Isotope is different atoms of the same element with different numbers of neutrons, with a different number of neutrons. So electrically charged, they're still the same, positive, negative, but they have different masses. Okay, so we can talk about, for example, uranium. Remember the isotope notation is you put the atomic number on the bottom. So 92 is uranium, has 92 protons, and then there's a uranium-238. These are both very famous from nuclear power and nuclear energy. and there's a different one that's a uranium, still 92, but it's 235. So 238 has 3 more protons than 235 does. So I'll write that here. I didn't expect you to write all this for your definition, but I'm just, again, we're going over these so we really solidify in our minds what these things mean. Electronegativity is the energy required to remove an electron from its atom. And there are first, second, third, fourth ionization energies. We'll talk about that next week. Okay, and alternately you can think of it as, this is just a colloquial, this is not the formal, this is really the formal definition, but it's how much does an atom want to hold on to its electron. If it has low ionization energy, it really doesn't want to hold on to its electron very much. Okay, so those are the definitions. We'll have different definitions on different days. Okay, we're going to do a couple more of these, constructing either molecules or formula units, and figuring out atomic mass and molar mass, and number of atoms and molecules in them. And then the second one, I'm going to do something a little different, and I'll show you that. All right? Okay, so let's go ahead and do this. So first, number of atoms. We're looking at this compound down here, and it is an ionic compound because it has a metal and a non-metal, so it's ionic. It does not form a molecule, it forms a formula unit. It's like one apartment in an apartment building. You can't tear it out of the apartment building, but it's the simplest unit in that apartment building, and this is the simplest unit of this ionic compound. So the number of atoms of iron, we have 1 because there's no subscript. That means there is 1. Chlorine has 3. And this 1 plus this 3 produces 1 of these. If you want to make a tricycle, you need 1 seat and 3 wheels to get 1 tricycle. Okay. All right, the atomic or molar mass. So we go to our periodic table, and I'm using a different periodic table, so I'm assuming my rounding is going to be what yours is showing. If it's not, go ahead and use what yours shows. Chlorine, mine's going to 5 significant figures here, so and it's 35.453. Now I have to multiply this one by 3, this one times 1, so it's the same, and that's going to give me okay, that's going to give me 106.36. So 106.36, and this one up here gave me 55.85. And you add those two together. Now you do add these, and I get 162.21. And again, this is in, first of all, we're not rounding it, and it is in AMU. So that's AMU. So that is the mass in atomic mass units of this formula unit right here. If you want to call it a molecule for right now, that's okay. So that basically means that's roughly how many protons and neutrons it has together, is 1 single unit of that. So moles, all we're saying for this is we want to multiply, all we're saying for these two things right here is we want to multiply them by 6.022. We need a big basket, so we have enough that we can actually see and measure and weigh. So we're going to take that and we're going to bring that over here. So this number becomes this number. I'm multiplying 1 atom of iron times 6.022 times 10 to the 23rd to give me 1 mole, this many iron atoms. I'm multiplying 3 atoms of chlorine by this number to give me 3 times 6.02 times 10 to the 22 of those. So now I have 3 moles, and I'm multiplying 1 mole of the compound to give me, one formula unit of the compound to give me 1 mole of the compound. So the numbers simply convert over. All right. For molar mass, you take the numeric value in atomic mass units, and you simply write it over here, except now it's in grams. A unit of measure that we can work with because all of our scales are calibrated in grams. This is 106, and that's the magic of Avogadro's number. Any other number other than 6.022 times 10 to the 23rd, and these two numbers would be different. You'd be multiplying this by something else, so you'd end up with something else here. You'd be multiplying this by something else other than this, so you'd end up with something else there. So to make these numbers match up so they're really easy to work with, that's why they chose this quirky looking number up here. So same thing down here is 162.21, and that's in grams. And now just to cement what we're dealing with in terms of atoms and molecules, if I have 1 mole of Fe, then that means that I have 6.022. Remember, a mole is a number just like a dozen. You can have a mole of anything. It doesn't matter what element or compound you're dealing with. 1 mole is that number. 3 moles is 3 times that number. You don't need to do the arithmetic here. Just understand the concept. Okay, and then finally, I get 1 mole of the compound. Okay, so now we're ready to run some numbers down here. So what you're looking at really is these last 3 columns here. And everything is referenced to 1 mole of our compound. So for 1 mole of our compound, I need 3 moles of chlorine. For 1 mole of the compound, I need 1 mole of iron. For 1 mole of this compound, I need this mass, 55.85 of iron. I need 106.36 of chlorine, that many grams of chlorine. And it will give me, 1 mole will give me this mass of the entire compound. And similarly, I need 1 mole here. I just counted out the atoms there. So let's go ahead and do this. So how many moles of Fe in 3 moles of FeCl3? So if I need 1 cup of sugar to make 1 cake, then I'm going to need 3 cups of sugar to make 3 cakes. So how many moles of Fe in 3 moles? Well, it's a 1-to-1 ratio, so if I multiply this by 3, you always start by multiplying this by whatever it's asking down here. So 3 times 1 here is 3, so I take that 3 up here, and 3 times 1 is 3. So I need 3 moles. And get used to writing it. Okay, I'm using the way that mole is written in chemical equations without the E on the end, and then the compound. It's always unit of measure and compound. Okay, next. How many moles of Cl in 3 moles of FeCl3? So in 1 mole of FeCl3, there's 3 moles of chlorine. So if I want 3 moles of this, I multiply this by 3, and that means I have to multiply this by 3. So 3 times 3 is 9. So there's 9 moles of chlorine. You need 3 times as much chlorine as the moles of FeCl3 of the compound. Okay, now how many grams is 3 moles of FeCl3? Well, it's just asking me what is the mass of that compound. Excuse me, no it's not. It's asking me what is the mass of the compound. So if I want 3 moles, I have to say this times 3 is going to give me 3 moles of FeCl3. So the mass in grams is 3 times this number. So write this out as a complete sentence so that you tie the two together. There are, and I'm going to do the math on this, 3 times 162.21 equals, so that's 486.63 grams, unit of measure, of the compound, Fe Cl3 in 3 moles. Okay, so there are 486.63 grams of the compound in 3 moles of that compound. Okay, just multiply both things by 3. How many grams of Fe in 3 moles of FeCl3? Okay, so let's write these out as complete sentences, even though we have the questions there. Okay, so how many grams of Fe in 3 moles? So if I want 3 times this, I come up to Fe, and this column is moles, this column is grams. So that's how many grams in 1 mole. So I need 3 moles of this, I need 3 times as much of this. So I'm going to do that multiplication, and we get there are 167.55 grams of Fe, of iron, in 3 moles, and even though it's plural, you would just write MOL, of FeCl3. Okay? Next question. How many grams of chlorine in 3 moles of FeCl3? So in 1 mole of FeCl3, there's 106.36 grams of chlorine. We needed 3 moles of that, and that's the total for 3 moles. So I need that much chlorine for each mole of FeCl3. If I want 3 moles of that, I need 3 times that number. So 3 times 106.36 gives us 319.8. So there are adjust it for you. There are 319.08 grams, unit of measure, chlorine, substance that you're talking about, in 3 moles of FeCl3. All right. How many moles of Cl in 0.52 moles of FeCl3? All right, so in 1 mole of FeCl3, there's 3 moles. So if I'm going to multiply this by 0.52 to get 0.52 moles, I multiply this by 0.52. So we'll go ahead and do that. And 3 times 0.52 is 1.56. So there are 1.56 moles of chlorine in 0.54 moles of FeCl3. Now notice that up here you have 3 times as many moles of chlorine as you have of the compound, 3 to 1. And you'll notice this relationship is still 3 to 1. This number is 3 times this number. So no matter how you scale it, you should have 3 times as much chlorine as you have the compound. All right, and finally, how many grams of Fe in 1.42 grams of FeCl3? Okay, so this one requires a little bit of your math knowledge. So let's look at what's going on up here. For every 162.21 grams of FeCl3, I need 55.8 grams of iron. In other words, this number is roughly, not exactly, but it's roughly a third of this number. 55 is roughly a third of 162, just roughly. That means if I don't want 162 grams, I only want 1.42 grams of FeCl3, then I need about a third this number of that. Okay? Again, let me say that again. If I want this much of the compound, I need this much iron. This is about a third the mass of iron as the mass of the compound. The mass of the compound is about a third iron. But if I don't want this much, I only want this much of the compound, then I need about 1/3 that mass of iron. So the way we do that, and you've done this at some point in your math classes, is set up a proportion. So the proportion would look like this. 55.85 grams of Fe is to, we're setting up a ratio, is to 162.21 grams of FeCl. And remember, this ratio, or this proportion, this ratio can be read as per, PER, or for every. So there's 55.85 grams of iron for every 162.21 grams of FeCl3. So on the top, we have our mass of Fe, and on the bottom, we have our mass of Cl. Of the compound, FeCl3. Okay, so over here, I'm going to draw a second ratio, and we want to know how many grams of iron, so that's our question mark, or you can put an X, for every 1.42 grams of FeCl3. Again, we're just in cooking class here. We're scaling things down. Okay, we don't need to make enough cupcakes for an entire school. We just want to make some for our class. We only need this many. So we're going to need a lot less of the ingredient up here. So what you do is cross multiply and divide. You cross multiply these two, and then you divide by this one. Or if you just like the algebra principle, you multiply top of both sides by 1.42. It cancels on this side. Your question mark is left by itself. But we'll go ahead and, either way, it gives you the same math. So we have 55.85 times 1.42 divided by 162.21. And what that gives us for our question mark is I get 0.4889, so I'm going to round that to 0.49. So there are 0.49 grams of iron in 1.42 grams of iron chloride. Notice that, again, we said that this number is about a third of this number, and I'm off screen, sorry about that. We said that this number was about a third of this number. If you look at it, this number is roughly a third of this number. Okay, not exactly, but roughly. So it's the same ratio. Okay, and now we're going to go on to another one, and we're going to move a little quicker through this one, or we're going to try at least. All right, so we have HNO3, nitric acid, and what we're going to do is H, we have one atom rather, nitrogen we have 1, and oxygen we have 3, and this 1 plus this 1 plus this 3 get together to form one molecule, covalently bonded molecule of nitric acid. Okay, so atomic mass. 1.01, we're not rounding it again, times 1, one day I'll get rid of that word, equals 1.01 AMU. Okay, next, same thing with nitrogen. Nitrogen is 14.01 times 1. And oxygen we've done many times before. Okay, and we add those up, we get 48, 58, 62, 62.02. 63.02, excuse me. 62, 63.02. Okay, and that's in AMU. Okay, now by now you should realize that all we're going to do to go from atomic to molar is just transfer these numbers over. 1, 1, 3, 1. All we're doing is multiplying everything here by 6.022 times 10 to the 23rd. Okay, and the molar mass is the atomic mass, but it's in grams. Okay, And next, and again, this is not terribly important in doing our calculations, but I just want you to be sure you know what you're dealing with is when you're dealing with moles in terms of actual atoms or molecules. So 1 mole is 1 mole. Doesn't matter what you're talking about, what substance you're talking about. 1 mole is 1 mole. This is 3 times a mole. Okay, now let's come on down here. I gave you some decimal numbers. That's the only thing that makes this a little bit different. And let's go ahead and work these. So again, everything is referenced around 1 mole of your compound, HNO3. So if you want 3 moles of this, you got to multiply any one of these things by 3. If you only want a half a mole of the compound, you multiply everything by 1/2. It's just that simple. You're just scaling things up and scaling things down. It's just easier to see on a table like this of what's going on. Okay, so here we go. How many moles of H in 4.2 moles of HNO3? Well, for every mole of HNO3, I have 1 mole of H. So if I want 4.2 moles of this, I'm going to need 4.2 moles of H. So okay, next up, how many moles of nitrogen in 0.312 moles of HNO3? So for every mole of HNO3, I also need 1 mole of nitrogen. So if I only want 0.312 moles of this, I only need 0.312 moles of that. In other words, you're matching up atom for atom, molecule for molecule, 1 to 1. And I should have written the word mole there. And there you go. Okay. Next up, how many moles of oxygen in 5.7 moles of HNO3? So I need 3 times as many moles of oxygen as I have moles of HNO3 if I want to create this compound. So if I want 5.7 moles of this, I need 3 times that number, the moles of oxygen. So if we do that multiplication, we end up with 17.1 moles of oxygen. Alrighty, now we're getting into grams. Okay, same thing except you're going to come on over here and deal in this column over here. So how many grams is 2.21 moles of HNO3? Well, it's just simply asking me what the mass of that many moles is. So if 1 mole of HNO3 is 63.02, then if I multiply this by 2.21, I multiply this by 2.21. So let's get our calculator and do that. And I get 139.27. So we'll talk more about this very important relationship between grams and moles. Basically, grams is the world that we live in. We can measure things in grams. We can't measure things in moles. It's too big a number. So this relationship is a really important one in chemistry. We'll be using it for the entire course. Okay, how many grams of H in 0.0034 moles of HNO3? So in 1 mole of HNO3, there's 1.01 grams of hydrogen. So if I only want 0.0034, I'm going to multiply this number. Sorry, I'm off screen. Let me say that again. In 1 mole of HNO3, there is 1.01 grams of hydrogen. Okay, everything over here relates to 1 mole of HNO3. If I only want 0.34 moles of HNO3, then I only need 0.0034 times this number of grams. Okay, so we're going to multiply that. And that gives us pretty much that same number, if you even to four digits. Okay, so there's 0.0034 grams of hydrogen in 0.0034 moles of HNO3. That's because the atomic mass of hydrogen is so close to 1 that it effectively becomes the same number. Okay? Next. How many grams of nitrogen in 0.087 moles of HNO3? So nitrogen, again, is a 1-to-1 relationship. So if I want 1 mole of HNO3, I need 14.01 grams of nitrogen. If I only want 0.087 moles of this, I need only 0.087 times this many grams. So do the math on that. And that gives us 1.22. Unit of measure and the substance, nitrogen. Okay, so again, let's look at this. Just be sure these numbers kind of make sense. 0.087 is a little less than 1/10 of 1. It's a little less than a tenth. So that means the grams of nitrogen is going to be a little less than 1/10 of the number I need to make a whole mole. So be sure that these relationships kind of make sense to you as you crunch the numbers. Okay, one more. How many grams of oxygen in 9.01 moles of HNO3? Okay, so for oxygen, I need 48 grams. It is 3 moles, but we're interested in how many grams. It takes 48 grams to make 1 mole of this. So if I want to make 9 moles of this, I need 9 times that much oxygen. Again, it's just cooking class. We're just scaling everything up. Okay, we want to make 1 cake. We need this much flour. If we want to make 9.1 cakes, we need 9.1 times this much flour. It's just a scaling exercise. All right, so we're going to do that on our calculator, and we got 9.01 times 48, and that's 432.48. So 432.48 grams of oxygen in 9.01 moles of HNO3. All right, and that takes care of that. We're going to practice these constantly, and this is really going to be important in chemistry. Okay, so I'm looking at this video being at about 40 minutes. It's getting a little long, so what I'm going to do is I'm going to solve the balancing equations, which is really the centerpiece of today's assignment. I'm going to solve that on a different video, be posted right on the same day 14 as this video. Okay, so I'll see you on that video.